the recording.
All right, so, thanks for coming back. So we'll continue the journey on non-invertible symmetries. So this morning, I reviewed for you this notion of the general notion of symmetry as topological operators. And we saw briefly how this the ordinary symmetries associated with continuous groups and discrete groups fit into this framework. And now we're going to generalize that using this based on this picture of symmetries as topological operators. And on dimension, so topological operators, and in the morning we discussed the case when the symmetry is associated with a group, and this is defined by a topological operator on the codimension 1 manifold of a spacetime. We're ready to generalize. The first generalization that retain the feature of being topological as well as some structure of a group is the notion of p-form symmetry, a high-form symmetry, generally a p-form symmetry. Okay. And this is realized by a higher codimension. In other words, p codimension. Actually, in my notation, will be the p plus 1 codimension topological defect. Okay. So instead of defining a topological defect defined on the codimension 1 manifold, in general, you can have a topological defect defined on a higher codimension manifold, and they generate a p-form symmetry, and the p enters into codimension in this way. Okay. And the particular example is the one-form symmetry. In four-dimensional gauge theories. And historically, they're known as center symmetry because the corresponding group coincides with the center of the gauge group. Okay. And in this case, p is equal to 1. And the generators are two-dimensional topological operators. And they are generators, they're the unitary operators correspond to the one-form symmetry. And the operators in the theory that are charged under this one-form symmetry are Wilson lines. Okay, this is the kind of a characterizing feature of higher form symmetries is that the charged objects are no longer local operators or particles, but rather are extended objects such as Wilson lines. Okay, and if you want to think about dynamical objects in your theory, think about say strings. Okay, they will be charged under this one-form symmetry. This is generalization number 1. Another generalization, as you probably already guessed from the title of the lecture, is to consider non-invertible fusion, or non-invertible, which come from general fusion. Okay, so previously, the topological defects, as I said, the symmetry are characterized by topological defects, their fusion, and how they act on local operators. How they act on local operators. In this case, it's generalized to case of how they act on these extended operators. And the fusion previously always takes this form. Okay, they follow some group multiplication law. Okay, instead of generalizing on the codimension, we can generalize this notion of a fusion product to something more general. So I'll denote two such topological defects by Li and Lj, okay, because I'm staying in 2 dimension, and the corresponding topological defects are 1-dimensional, represented by these lines. We know these two topological lines, because they're topological, looked from far away, they look like a single topological object. Okay, and in general, it could be reducible. So it could be decomposed into a sum of individual topological lines. Okay, without assuming there's underlying group associated with this topological defects. Okay, and the point that on the right-hand side of this fusion product involves multiple topological defects rather than a single one is a signature of non-invertibility. Okay, so when you talk about group multiplication law, of course, you always only have a single term on the right-hand side. Okay, there's no meaningful decomposition. And as you will see,
sorry, can this be viewed as an generalization of the OPE expansion?
That's a very good question. Indeed, I'll make a comment in relation to the OPE of more general defect in a moment. Yes, yes. So this is a special case of OPE expansion involving extended objects, here line defects. Yes. Question?
Oh,
no. Why are there no signatures of the indices I and j on the right hand side?
Right. So so this what k appears here depends on I and j.
Okay.
So this step implicitly depends on the choice of I and j. But I'm being kind of a schematic here. Later we'll write explicit equation. And in particular, that's a good point. So some of the lines here could be degenerate, meaning that I'm summing over. I'm just doing arbitrary decomposition here. So I'm not assuming these are each one appearing here is irreducible, for example. So if you write the right-hand side in terms of indecomposable lines, the coefficient may also carry the degeneracy of how many times they appear. We'll be precise about that later.
Thank you.
Here, just schematic. So the moment you have this non-trivial sum, having more than one term appear on the right side is already a signature of non-invertibility.
Sorry.
Question?
Well, the definition of having more than one term needs a definition of some like building block. No, like a sum of lines is a line. No,
that's right. That's right. So that's a very good question. So as we'll get to that, from what I've told you here so far, there seems to be no kind of a physical meaning of how I split the right-hand side, right? For example, why we say like when I have a single line as before, why can't I split a single unitary as a half, right? Here is obvious because if you take a half of a unitary, it's not a unitary anymore. Here we'll also see that there's a constraint precisely how to decompose this coming from the locality of the quantum field theory. Okay, so you can not arbitrarily scale your line defect. Okay? That's constrained by locality. Okay. All right, so let me now come to this question that was just asked. In relation to a notion of OPE between these extended operators in the more general context. Okay, so indeed, this can be thought of as a special case of OPE between defects. In this case, I'm focusing on line defects, say int equal to 2. But this is a general notion you can consider in higher dimension. But in general, the OPE of the line defect is much more complicated. Okay, for example, just to make connection to existing knowledge about defects, let's consider an example of conformal defects. So a large class of non-trivial defects are these conformal defects, conformal defect lines. Int equal to 2. Okay, so these defect lines are again kind of denoted by this in the same picture, but let me emphasize this is a conformal defect in general. Okay, and it is defined such that the stress tensor, so in general, it actually can be an interface. Okay, it's defined such that the stress tensor on this side, okay, satisfy this relation. No, let me think about this this direction. So this is the z plane, and for convenience, I'm calling this direction the imaginary z direction, okay, which is the location of the interface. Okay. In general, there's a discontinuity in the stress tensor for a conformal defect. Okay, even for in the same theory. Okay, the discontinuity in the stress tensor is captured by what's known as a displacement operator. Which is the operator on the conformal interface. Let me call it I. Okay. The special case of topological defect correspond to the case when D is trivial. Okay, so the stress tensor is fully continuous across the defect. Now, for the general class of conformal defects, there's this notion of OPE that you can discuss. Okay, so I take I1, I2. There are two conformal defects. Okay, and that's kind of the picture that you would want to have also for conformal defects, a similar picture as that. But there's some important differences. For example, even if you take this two to be the same defect, okay, with opposite orientation, and you expect the identity defect to show up, the trivial line to show up here, okay, but this coefficient would involve divergences, in particular from the Casimir energy. So considering OPE will be corresponding the limit where you take the two defects close to one another. And you will have this Casimir energy divergence that's proportional to a cosmological constant term integrated over the defect, okay, over the line. And moreover, you have subleading divergences due to relevant operators on the line, okay, from this fusion product. So it's physically very distinct from what happens here the moment you have this discontinuity. The discontinuity in the stress tensor is what gives rise to this Casimir energy. Okay, which is essentially measuring like the some kind of imbalance between the stress tensor inside this region and outside. Okay, and because in a non-topological case you have this divergence piece, and there's the structure of this fusion, although you can write it down, but it's much messier. Okay, and in some special cases, for example, if your system has supersymmetry, okay, in that case, because of the contribution from bosonic fermionic degrees freedom, and for supersymmetric line, you can achieve the special case where this Casimir energy pieces of divergences vanishes. Okay? And this is why in supersymmetric theories, it's meaningful to talk about fusions of supersymmetric Wilson lines and so on. And this kind of fusion product is well defined. Okay?
Sorry.
And you may be able to derive similar relations, for example, from localization.
There is no way to regulate this divergence then.
Sorry?
There is no way to regulate the divergence.
You can, but you know, like if for kind of a generic theory, there are many divergences over here for each of these relevant operators. If there's only a single divergence coming from the cosmological constant term, then that's more kind of a there are ways to deal with, but with facing the entire tower of subleading divergences from relevant operator means dimension smaller than 1 in this context, okay, on the line. There's no obvious way to achieve a meaningful answer. Okay. Question?
Sorry, this might be a naive question, but is this divergence related to both the UV and IR structure of the theory? Because in one case, you're taking delta to 0, which is the short distance structure, but you're also integrating over some non-compact direction, presumably.
Right. So here you can make it compact, but the divergence stays. It's because of the limit.
So the divergence is mainly UV divergence.
That's right.
Thank you.
The Casimir energy. Okay. So that's just a quick comment. All right. So let's fulfill this promise to provide some toy example before we jump into general structure. Some toy example for non-invertible symmetries. Okay. The toy example is not going to be the toy example of this invertible symmetry will take place in a very simple theory, which is the discrete gauge theory. With gauge group, a discrete group G. Okay. I think someone of you already asked me about this during the discussion, informal discussion. So in this case, there are interesting topological operators, which are extended objects. These are Wilson lines. And these are the Wilson lines that you would have. They are just the analog of the Wilson lines you would have for a continuous gauge theory. Okay? So they are labeled by representations of the corresponding group. In particular, the indecomposable Wilson lines are labeled by dReps of the group. Okay. So explicitly, you can write them in terms of the exponential of your gauge field over a curve. Okay, as follows. Now, in general continuous gauge theory, like in Yamil's theory, okay, this Wilson line would not be a topological object. Okay, that's because the connection in general is not flat. But here it's topological because discrete gauge fields are always flat. Okay, it doesn't support, discrete gauge field cannot support any curvature. As a consequence, this provides possible realizations of the topological defect operators that we may interpret as symmetries. Okay? And they claim they're non-invertible. They give rise to non-invertible symmetries. If G is non-abelian. Okay. So what is the simplest? There's a question? Yes.
So what happens when the connection is not flat?
So when the connection is not flat, then this Wilson loop is not going to be a topological defect, but they will fall. It can fall into this realm of conformal defects. And as I said before, their fusion in general is much more complicated. There are these divergences, and from these divergences, there's the regularization ambiguities. But in special cases, like with supersymmetry, you can still have this well-defined fusion products when all the lines preserve the same supercharges.
And how can you assure that in this case you have a flat connection?
Oh, it's essentially by construction. If you're talking about discrete gauge field, there's just no curvature.
Okay. Yes.
Discrete gauge field backgrounds are classified just by Hall analysis. Sorry, just by the transition functions.
Thank you.
Sorry, what are the connections for a non-abelian discrete group?
So this is the same thing that I drew before. To specify a gauge field background, equivalent to specifying the gauge connection for a discrete gauge field is equivalent to decorating your partition function with a network of symmetry defects. Each of them will be labeled by this UG, okay, where G is element of the group, okay, and they're joined by these topological junctions, which we introduced in the last lecture. So this specify tiling of your spacetime by networks like this specify a particular gauge connection background. And the discrete gauge theory means that you're summing over all these configurations, right? And if you don't like this notation, well, okay. So this is I think this is the best I can do for general non-abelian groups. For discrete abelian group, sometimes you can introduce some kind of Lagrange multiplier field and write everything in terms of U1 gauge field. But this will be the what we need to do for this general non-abelian discrete gauge groups. Okay. So another question?
As you also draw in this picture, and as you presented this morning,
yes,
there are maybe two different point of view on fusion, both as picking defect as stacking on the same manifold,
yes,
or as junction as you draw
that's
here.
right. That's right.
Is it obvious that this is exactly the same thing? And I mean, maybe for lines, it is almost obvious because you can put lines only on trivial manifolds, but for higher dimensional defects, you might put your symmetries on different two-dimensional manifold, for example. And I don't know how to see that it is the same.
Yes, you caught me. That was correct. So when I draw this picture, this represents discrete gauging in 2 dimensions. There's a similar picture, but it's harder to draw for the 3-dimensional gauging. In that case, it will not, the basic junction will not be of this shape, but it's similar basic building blocks, and similar in higher dimension.
Okay, so but these 2 points of view are always the same. Both as stacking defects and with junction are always the same.
No, so as I said before, you have the topological defects, and they satisfy some fusion rule, and on top of that, there are these junctions. The existence of junctions can be inferred just from the topological property of the lines. Okay, but there are some extra data, which is the specifying each junction. Okay, and that goes into defining this gauge theory background. The key point is that the freedom that you have in defining these junctions will not affect physical quantities like anomalies associated with the corresponding symmetry. So in this case here, for example, I'm talking about the discrete gauge theory, in which case I have dynamically gauged the group. So I'm implicitly already assuming there's no anomaly associated with the symmetry in this setup. Okay. All right. So let's get back to this claim. So perhaps the simplest example of a non-abelian group is the case when it's the permutation group of 3 elements. Okay. In this case, we have 3 irreducible representations. The trivial representation, I'll write as 1 for the moment. It will become clear why I call it 1. And there's an additional 1-dimensional non-trivial representation, that's the sign representation. Okay. And then there's a vector representation, which is the 2-dimensional representation for S3. Let me call it V. Okay. And as is true for Wilson loops in general, okay, you can decompose at the level of the representation data associated with the gauge group. We can decompose the fusion product between 2 Wilson loops into Wilson loops labeled by the representation that appear in the tensor product. Okay. So in particular, the Wilson loop associated with the sign representation, when you fuse with itself, you just get identity. That's because the tensor product of sign representation with itself is the identity representation. Similarly, identity, when you fuse with the sign representation, it does not change the representation. And the same is true for the vector representation. Okay. So far, I'm writing fusion rules where only 1 term appear on the right-hand side. And that's a signature of so far we're just uncovering some invertible symmetries in the theory. non-invertible symmetry will be generated by the Wilson line, the Wilson loop associated with the vector representation. Now the key is that the tensor product of the two vector representation of S3 decompose into three representations. All these three representations appear in the tensor product. As a consequence, on the right-hand side, you have this combination of Wilson loops appearing. Okay, and this is the non-invertible symmetry that we promised in this very simple toy theory. Okay. And if you are still confused about something that I said before, let me just focus on the case for D group 2, and then this is literally the picture that it means for, this is the literally kind of the network you sum over to define this discrete gauge theory. Okay, but this construction, what I was trying to emphasize before is that this construction works in general dimensions, and you always, for any discrete gauge theory in any dimension, you will have this non-invertible symmetries generated by these Wilson lines. Okay, as long as the gauge group is non-abelian. When it's abelian, all the irreducible representations are one-dimensional. And you will not have this non-trivial tensor product that involve more than one term in the decomposition on the right-hand side. Okay, and this is a very simple model that realizes this symmetry, and it turns out that this symmetry is usually denoted by S3 rep S3. Okay, meaning that the individual generators of the symmetries are one-to-one correspondence with representation, irreducible representation of S3. Okay, and later we'll see this kind of trivial symmetry will show up in the interesting two-dimensional CFT, namely the three-state pulse model. Okay. So here I discussed the kind of trivial example, a trivial theory where some non-invertible symmetry shows up. But the general lesson is that given non-invertible symmetry can show up in many theories. In particular, we'll see that show up in more interesting theory, the three-state pulse. Okay. Once we have settled this very simple toy example, let's start with some generality of non-invertible symmetries to spell out the general structures in more detail. Okay, and once again, I'll be focusing on dimension 2. Okay, and as I've alluded to before, the mathematical structure here, we'll see the mathematical structure here generalize the groups to what's known as the fusion category. Okay, and we'll unpack the ingredients that go into this definition step by step. So the basic starting point of defining a non-invertible symmetry in two dimensions in general quantum field theory is to first specify the set of topological defect lines. Which we will abbreviate as TDL. Okay, and it will denote by Li individually. Okay. And analogous to the fusion rule that we wrote before, and we generalized to the case when there are more terms appearing on the right-hand side, this topological defect lines generally satisfy some fusion algebra or fusion ring, which tells you how to decompose products of these generators in the fusion product. And when I write the equation like this, it should always be interpreted in this way. Okay, so you are taking these topological defect lines to lie on manifolds which are homologous. Okay, and you're taking the limit where they go to one, they approach one another, and you decompose in this configuration into the individual topological defect lines. And in particular, among this set is this distinguished element, which we'll call 1, that correspond to the identity line. or corresponding to the case there's no insertion at all. Okay, and you're free to apply this to any, fuse this with any of the lines over here, and it will return to you the line that you started with. Another notion is something that's already asked in the context of discrete symmetry that generalized beyond the fusion ring is the notion of topological junctions. Okay, the existence of topological junctions can be inferred from the topological property of these lines, but to specify these junctions individually requires additional data. Okay, so these topological junctions are defined as follows. For any line, I call it L3, that appear in the fusion product between L1 and L2. So whenever I write the product of a line, it's interpreted as, in the sense, a fusion product. Okay. For any line that appear in the fusion product, you have a topological junction of this type. Generalizing the topological junction that we saw when these are lines that generate group-like symmetries. Okay. The junction relies on a specification of this point. Okay, so it can be thought of a point operator, which are denoted by V. Okay. In general, when you specify the external topological defect line, there may be multiple choice of V, and this V, in general, is a vector in the vector space, which we'll call the junction vector space. Okay, topological junction vector space to be precise. Okay, and this topological junction vector space, because these are point-like operators, you can equivalently think about this as kind of a TDL or topological defect line changing topological operators. Okay. In particular, in a special case, when L2 is identity, V will be the topological changing operator between the defect line L1 and L3. And in general, V will be the topological defect changing operator between the fusion product L1, L2, and L3. Okay. And later, we'll give a more precise kind of a picture for what this topological junction vector space is when we discuss this topological defect lines in two-dimensional CFT. Okay. The last ingredient to fully specify this notion of fusion category is the notion of F symbols. Okay. And this captures possible factors you get from a topological change, a topology change in a network of topological defect lines, similar to the phase that we encountered when we change a network of part of the the background, describing a color of the background for a discrete symmetry. Okay, so so this topological change is commonly referred to as an F move, okay, which is the basic move to change the topology of this kind of diagram, describing a two-dimensional background for the discrete symmetry, and also generalized to this background of TDL network. Okay. So I'm just redrawing the diagram we draw before, but in a different way. Okay. That's conventional in convention to the literature. So 1, 2, 3, 4 denotes 4 topological defect lines. Okay. And A labels this internal topological defect line. Okay. And all these junctions are topological junctions, so they're specified implicitly by some specific vector in this vector space. Okay. The F move corresponds to a topology change in this network by reconnecting the second topological line to another leg. Okay. And in general, some other intermediate topological defect line may appear over here. And this change of basis is captured by some numerical coefficient known as the F symbol. Okay. So here, this thing can be thought of as a matrix. The 1, 2, 3, 4 are external labels that specify the external lines that enter into this diagram. And this indices specify the change of basis between these two configurations. Okay. So why do I say this is a change of basis? What I mean precisely is that this is a change of basis in the junction vector space between 4 external lines, L1, L2, L3, and L4. Okay. So you think about this pair of trivalent vertices as a basis for the topological junction between 4 external lines. Okay. Because there are 2 ways to resolve this 4-point junction. There are junctions. So there are 2 that give you 2 preferred bases for this space. And this F matrix captures the change of basis.
Right.
This question?
Can you comment a bit about operational change of this arrow? Because in the first picture you draw the two ingoing, like in the vertex you have 2 ingoing and 1 outgoing, but in the other diagram you have 2 outgoing and 1 ingoing.
Sorry, which picture?
Like for example, for this picture, like
Picture?
Yeah, how important is it the 2 ingoing and 1 outgoing?
So it's just because I want to make sense of this notation. So I can draw ingoing, and then it will be the L3 bar. I'll come back to that. Yeah.
You will define what you mean by bar.
Yes,
okay.
Yes. Okay. Thanks for the question. All right. I think I can use this.
Another question.
Yes. Question.
Can you explain again why there's a whole vector space of junctions?
Right. Okay. So it's not. I think that notion is not completely clear at the moment, but you can think about this way. So the point is that this is like a point-like operator. Okay. So having 1 junction, you can multiply this point-like operator by arbitrary complex number. That's still topological. It's just a different way to define this junction. So if you have 2 independent such junctions, then you have a 2-dimensional complex vector space, and that's one way to think about it. Later, we'll give a physical interpretation of how this junction vector space comes about in the 2-dimensional CFT. It will be related to the Hilbert space of the 2-dimensional CFT on the circle with defect points. And they will be characterized by specific states in that Hilbert space. It's a subspace. We'll make that precise.
But in order to define this F symbol, why don't you need to specify the junction?
Very good, very good. So I cheated a bit. So here, as I said it, but I didn't write it because it just makes the equation more complicated. So on the left-hand side, there's a choice of V1 and V2 over here.
Oh, okay.
Okay, and on the right-hand side is also the choice of junction vectors here, V3 and V4. And this matrix will involve these additional indices V1, V2, and V3, V4, and you're summing over all these choices. And for simplicity, I'm just drawing the case when the junction vector space are 1-dimensional. Okay. So that the information is completely captured by this coefficient. Otherwise, there's a further indices.
Is there some interesting case in which the junction are always 1-dimensional, or
So yes, of course, yeah. So we'll come to that. For example, the duality defect, which shows up in 2-dimensional IC model as well as in this 3-dimensional and the 4-dimensional gauge theories. They all fall into this category, that having a 1-dimensional junction vector space. Okay? As we'll explain, the dimensionality of this junction vector space will be tied to the coefficient in the fusion ring when you write to the right-hand side in terms of indecomposable objects. Okay, and whenever the fusion product is such that only coefficient 1 shows up in the decomposition, that's the case. That, as we'll explain, that corresponds to the case when this is 1-dimensional. Okay. Thanks for the questions. But I was slightly jumping ahead, so if you didn't understand that last comment, don't worry, we'll come to that. All right. So these F symbols are not arbitrary. Okay, so they satisfy some consistency condition. This is something that you can already kind of inferred from the fact that when you specialize the case when the defects are invertible, okay, this F symbol is nothing but the phase that we introduced before that captures the anomaly associated with the corresponding discrete group-like symmetry. Okay, and as we said before, the anomaly is subject. The anomalous phase is subject to this consistency condition that essentially tells you that it's a cocycle. Okay, and that's where the group cohomology classification of anomalies comes in. And here we can be more explicit and recall where the consistency condition comes from. Okay, the consistency will come from looking at a five-fold junction. So it's a topological junction involving 5 external legs. Okay, so for simplicity, I'll not keep track of the arrow. Okay, and then there are 2 internal legs labeled by A and B. Okay, so this specify, if you once we specify the junction vector over here, this specify a particular junction in the space of between 5 external lines, 1, 2, 3, and 4. Sorry, 1, 2, 3, 4, and 5. Okay. Now there's a consecutive change of basis you can do. Okay, I think I was too ambitious with my space management. What I'm going to draw will not fit in that region. So let me move over here. Okay, we start with this diagram once again. 1, 2, 3, 4, and 5. Okay, A and B. And as I said, this specifies a particular junction vector in this junction vector space with 5 external TDLs specified 1, 2, 3, 4, 5. Okay, and of course there's various ways to resolve. So you can think about this as specifying the 1, 2, 3, 4. The choice of junctions living here. Okay, so this is what so this is the general junction, topological junction with 5 external legs. Okay, and this for any vector here is going to be element inside this big vector space. Now there are different ways to represent vectors in this space using the topological nature of this TDLs. So in other words, you can try to resolve this very singular looking junction into like a triplet of trivalent junction in this picture. Okay, and each different resolution will give you a different basis. Okay, for this junction vector space by considering arbitrary choice of internal legs over here and arbitrary choice of junction vectors at these threefold junctions. Okay, and there's a consistency coming from comparing this to the following. Okay, so let me draw it over here. So this is the famous pentagon equation. We can perform this change of basis, okay, given by this F move, okay, from this basis to this basis, okay, by using this F matrix. Okay, and we can do it multiple times. Okay, now do the F move focusing on this part. Okay, and you get to this picture. And we can do it again. Focusing on this part and apply the same F move, and we get to this picture. Of course, there will be different coefficient or different matrices that enter into each step, correspond to a different labeling of the external labels as well as the choice of internal lines that appear in that channel. Okay. But then the point is that going through this round, we establish the changeable basis between this basis for the 5-4 junction vector space and this basis for the 5-4 junction vector space. Okay, but there's a different way to reach the same changeable basis matrix, is to do first this picture, okay, which correspond to doing F move on this block. Okay, so you reconnect 3 with this other side of this diagram, and then do F move on this region, and you get to this basis again. And in this process, another different, the same as F matrix with different external indices shows up. And by consistency, because you're just discussing changeable basis between two special bases in 2 different ways, you must get the same result that schematically look like a product of 3 F matrices with certain indices that's been contracted is equal to the product of 2 F matrices going this way. Okay, and this is the famous pentagon equation, because this looks like a pentagon. Which is a generalization the cocycle condition for G symmetry. Okay, for invertible symmetry where G is discrete. And in which case the pentagon equation is the same as the cocycle condition that defines the G anomaly. Okay. So now we have introduced all the basic ingredients that define what is known as the fusion category. Okay. So it's not something mysterious. It's just some objects that generalize groups and knows about the anomaly associated with groups to the case where the building topological defects are non-invertible. Oops. Okay, I'll pick it up later. Together, so I was saying, the topological defect lines, their fusion junctions. So these are individual building blocks for this underlying structure, and F symbols. They lead to the fusion category. The structure of a fusion category. Okay. So this is just some references in case you have heard about the category before and you want to make connection to the notion of category in this language. In this case, the underlying objects for the fusion category are the topological defect lines. The fusion will describe the tensor product between these objects in this fusion category. The fusion category has, in particular, a structure of a tensor product. And these junctions leads to morphisms between objects in the fusion category, in particular between objects and their tensor products. Okay, and this is why the trivalent junction defines a morphism. Okay, and these F symbols are known as associators, which specifies isomorphisms between the tensor product of 3 objects. Okay. Okay. It actually has six external labels. That's why it's called also called a 6J symbol. And this fusion category structure, as we already saw from various parts of this structure, it generalizes discrete group symmetry. Okay. In particular, in a special case, when all the topological defect lines are invertible and corresponding to some group, the fusion category is nothing but the usual discrete group symmetry, but at the same time, keeping track of the anomaly through the F symbol. So it's in a sense more kind of contain more data than the group, but the data it contains is precisely what we care about in physics. There's an anomaly associated with discrete symmetry. And the second comment is that the structure of a fusion category is extremely constraining. Okay. Of course, if you don't introduce this non-invertible defects, then it's just as constraining as it is for constraining anomalies associated with a given group symmetry. Okay, but here the constraints manifest in the following way. Let me just give you an example. If you start from a set of topological defect lines which you postulate that describe some fusion category symmetry, and you postulate the fusion rule. Okay, for example, if you just postulate a single topological defect and you postulate the fusion rule of the form L squared is equal to 1, which is a trivial defect, plus n, which is some degeneracy, times L itself. Okay. This is only gives a fusion category for n equal to 0 or 1. Okay, so this is very surprising because why can't we have a single non-invertible defect that satisfies such a fusion rule? Okay, and the constraint is coming from the F symbols, and in particular the Pentagon equation that constrain F symbol. And the punchline is that when the n is so the story is that when n is large enough, there's just no solution to the Pentagon equations. Okay, and as well later we'll see, all the structure of fusion category symmetry would necessarily comes out from the locality of a quantum field theory. So that tells you that this symmetry is just simply not possible in the quantum field theory. Okay.
Sorry, I have a question.
Yes.
So does this constraint come from unitarity or it's independent of unitarity?
This statement is independent of unitarity. It's just, well, okay. So let me start. It depends on how unitary you want the theory to be. So to be absolutely sure, I think we're implicitly assuming some notion of unitarity, because if we forget about unitarity, then for example, the fusion products may have funny coefficients, and that would ruin this story. But here, the fact that we're talking about the fusion category actually relies on some notion of unitarity. That's a very good question. Yes.
Thanks.
Otherwise, there's this general notion of some pseudo fusion category, right? Very good question.
Sorry, when you look at the solution of the Pentagon equation, in which range do you look for F? Should be a phase? There is some condition.
Very good question. So very good question. Very good question. So as I mentioned briefly over here, there's for each junction vector there's ambiguity, right? Even if the junction vector space is one-dimensional, you have an ambiguity coming from the complex number. And if you keep track of an ambiguity in this equation, you see that depending on your choice of normalization of this vertex here and here, okay, that will change the F matrix. Okay, so in general, this F symbol is not completely unambiguous. Okay, but the statement here is that there's just absolutely no solution, whatever choice of normalization you take for the vertices. Okay, but in general, you will have family of solutions for the F symbols, but we only study them up to this equivalence relation, and that is the analog of the this exact cocycles in the context of a group cohomology. So the phase coming from the F move for the group symmetry case, okay, that's subject to ambiguities coming from the exact cocycles, and that is the physical origin of that is coming from the redefinition of this point-like operators. Okay. All right. Another comment I want to make over here is that just like in the case of groups, right? There are ways to classify groups, and that is known. Okay, so you may ask if there's a classification of this fusion category symmetries, and the answer is that mathematicians are still working on that, and there's no classification as of yet. except for low rank cases. Rank means the number of indecomposable objects, which we'll come to shortly. Okay. But on the other hand, from physics, as we'll see, we'll be able to produce tons of examples for the diffusion categories. Okay, so it's really down to the mathematicians to actually pursue a classification that would include all the examples we cook up. And lastly, it's related to the question there's some structure associated to the pentagon equation. Okay, that is up to this gauge freedom that we have associated with redefining each point-like operator that live at the junction. There's topological point-like operators. Okay, the pentagon solutions, the pentagon equations have only discrete solutions. Okay, so again, this is up to the gauge freedom that we talked about in redefining these junctions. Okay, and this is very nice. Mathematically, this is known as the Oaknienu rigidity. Okay, this is something that the mathematician have proved. Okay, so it says that the pentagon equation does not allow continuous family of solutions when you remove the potential continuous ambiguities coming from this redefinitions. Okay, and this is very nice because this is the similar feature that we have for anomalies. Okay, anomalies are quantized and they cannot change under continuous deformations. And because of this feature, they are bound to make non-trivial constraints on quantum field theories. Okay, in particular for RG flows, which is a continuous process. Okay. So that is the mathematical framework underlies this non-invertible symmetry in 2 dimensions. Okay. We have not really put in any physics. As we'll see, studying these symmetries in the context of 2-dimensional quantum field theories would make many of the structures more transparent, and it will also lead to additional physical information, which is not obvious at all from these basic building blocks. Okay.
And Ivan, just in principle, in 2 minutes, we should move to the discussion, but maybe you got a lot of questions, so you can take a little bit more if you want.
Oh,
how much?
This is already, okay. Yeah, I think if I can have, it can have 10 minutes.
Okay, I think that's good, yeah.
All right. So there's some extra structures. Let me explain. Coming from studying the symmetry in 2-dimensional QFT, okay, with this non-invertible symmetry. Okay. So to be explicit, we'll restrict to 2D CFTs. We'll discuss the symmetry in the context of 2D CFT. And this is not really a loss of generality because as we alluded to over here, the structure of the diffusion category is rigid. So 2D QFTs that's obtained from CFTs by RG flows is naturally captured by the statement we'll be making here. Okay. But the CFT or TQFT, which is a special case of a CFT. Okay. But the notion of a 2D CFT will help me to make some explicit statements using, so this is convenient because we'll be able to use radial quantization. And as we'll see shortly, they will help me to specify what these operators are in radial quantization. Okay, because in this case, in the CFT, I have radial quantization. On top of that, I have well-defined eigenvalues for the L0 and L0 bar generators for the conformal symmetry, and they are H bar and H. Okay. This is the only really where I'm using the CFT structure. Okay. All right, and the key, as I already mentioned, that leads to this extra structure in CFT for this diffusion category symmetry is the locality. Okay, and this is something true for general quantum field theory, which can be thought of as consistency in cutting and gluing CFT or quantum field theory binding function with observables. Okay, so you can cut and glue, cut your observable binding function with observable in different ways and glue them back together. It will lead to the same results. Okay, that's one notion of locality. Okay, one way to phrase the notion of locality. And as you'll see, this locality will lead to this fusion category structure, starting from the basic objects, the topological defects. Okay, all the others will just follow. First of all, so we start from the topological defects, which we postulate is as a symmetry in the theory. Okay, the topological defects act on local operators. Okay, and we can be quite precise in the context of two-dimensional CFT. So imagine you have a local operator over here. Okay, as I said before, the way a unitary operator acts on the local operator is by enclosing it. Okay. And because this operator is topological, it means that in particular it commutes with stress tensor. Okay, so it will preserve the conformal weight associated with this local operator, and it will produce another operator, which I'll denote by L hat, acting on operator phi. Okay, it's operator with the same H bar as the original operator before you act by the topological defect. Okay. And moreover, this also implies that the topological defects will map Virasoro primaries in the two-dimensional CFT to Virasoro primaries, and it will map the entire multiplets to multiplets. Okay. And equivalently, from the radial quantization, you can think about this picture as meaning on the cylinder. Okay. Where on the bottom of cylinder, you insert the corresponding state correspond to this local operator. So it's a primary operator. Okay. And this is a state inside the Hilbert space on S1. And this is the line insertion, okay, that acts on this Hilbert space that comes from this radial mapping. Okay. The coordinate change that you use in the radial quantization. And this is the equivalent meaning that tells you how, you know, this is why we use the L hat, because L hat can be also thought of as the operation of this symmetry defect acting on the states. Okay. So this is the, if you wish, this is the generalization of what Wigner wrote for unitaries, but now for this more general operation, linear operation L hat. So I just introduced the last another ingredient and questions. Okay. The other important ingredient coming from the quantum field theory in the presence of these topological defects is the defect Hilbert space. And this is the consequence of the locality of these topological defects. Okay. And this is the generalized notion of the twisted sector of a two-dimensional CFT that you associate with discrete symmetries. Okay. The idea is that you study again the theory on the cylinder, but you can choose to align the topological defect now in the time direction. Okay. In which case the Hilbert space gets deformed, and the general state inside the Hilbert space, I'll denote it by psi. Hilbert spaces get deformed, okay, into this twisted Hilbert space. In the special case when L corresponds to a group-like symmetry defect, this is nothing but the Hilbert space with the twisted boundary condition imposed on the spatial circle. But in the case of a non-invertible defect, because of locality, you can still define this defect Hilbert space. And by the same conformal map that relates the radial quantization to the cylinder, this is equivalent to specifying this operator is equivalent. Sorry, specifying this state is equivalent to having a local operator that sits at the end of topological defect line. Okay. And once again, because of the topological nature of these lines, this again fall into representations of the two copies of Virasoro symmetry. Okay. And in particular, we'll assume the following condition, which is a physical assumption. Let me call it the typo condition. That is only the identity line can end topologically. And this is equivalent to having a faithful representation of the symmetry, in this case, the non-invertible symmetry generated by this topological defect on the Hilbert space on S1. Okay. The reason is that if other topological defects can end topologically on operators, so in this case, psi in general is an operator with h and h bar, that's not equal to 0, 0. Okay, so it's not. So in the case of a topological junction, it will be the special case when h bar equal to 0. Okay, but in general, this is not possible. And indeed, for CFTs, we want to impose the condition that this is always not possible. So having h and h bar equal to 0 for psi is always impossible when the topological defect line is not an identity, and that's equivalent to requiring the symmetry that you are studying to be represented faithfully on this Hilbert space. Okay. I think I'm running out of time, right? So maybe let me stop here and answer questions, and we'll catch up next lecture.
Okay, so let's thank the speaker. And before we move to the discussion, I think there is a group picture to be taken. I don't know if there are some instructions. Just the bottom, a bit. Yes. Leave it. Just maybe turn it off. Okay. We cannot see the bottom part, but is it scrolling down continuously? Yeah. I see. I see. Okay, that's good.
Can you hear me okay?
Yes, yes, we can hear you very well. So we will start in about 5 minutes.
Okay.
No, because it's continuous scroll. If anybody is missing this, was found on a desk. There was a watch that was found on a desk. If somebody is missing it, please come to me. Otherwise, I will leave it some. Okay, Kevin, as you probably know, it's like 1 hour of lecture, and then there will be 15 minutes for informal discussion.
You just let me know when I should start.
Yes, no, people are still entering the room. The volume of Zoom? Oh, I don't know. Okay. So I guess the time has come. So we are very happy to have Kevin Costello joining us remotely from Perimeter Institute, and he's gonna tell us about twisted holography. So I will just start the recording. And please, Kevin, take it away.
Okay, thank you very much. And I'd like to thank the organizers for the opportunity to give these lectures. I'd also like to apologize that I wasn't able to make it in person. I'd appreciate it if, I'm not entirely sure the level and background of the participants. So I really appreciate any feedback about how fast I'm going and the level of the material. And interruptions are very welcome. So what I want to talk about is, well, the title is Twisted Holography. So what I'll talk about is based on work by many people. And it's a way similar to in Matthias' lectures. Twisted holography is a way of getting really sharp, exact results from a supersymmetric subsector of ordinary holography. In Matthias' lectures, he's not considering a supersymmetric subsector, but there are also exact results. So let me remind you a little bit about the background. So the original ADS CFT correspondence, we've all heard a great deal about it, but it's important to recognize that the original correspondence is still very much conjectural. Okay. So it's a conjectural duality between n equals 4 super Yang-Mills and type 2b supergravity on ADS 5 times S5. So the reason one should view this as conjectural is that both sides of the duality are incredibly difficult to understand. So on the gauge theory side, n equals 4 super Yang-Mills, we're supposed to be studying strongly coupled gauge theory. Strongly coupled, constructing rigorously, or in any sense, a strongly coupled gauge theory is probably the most difficult problem in mathematical physics. It's one of the Clay Millennium Prize problems. So this is really out of reach of any mathematical techniques. And on the other side of the duality, when studying type 2b string theory and ADS 5 times S5, this is difficult for two reasons. If one wants to take the supergravity approximation, then we're studying quantum gravity. Quantum gravity is, of course, hard, because it's not normalizable and so ill-defined at the quantum level. On the other hand, one might try to think of it as a string theory. String theories are the way of defining quantum gravity. But it turns out that string theory in ADS 5 times S5 is also very challenging. The reason I don't want to get into, but it involves the fact that this is a Ramon background. So, of course, people have done lots of checks, and there's like very heroic, extremely difficult computations at both sides. So it's very plausible that this works. So what I'm going to talk about today is a subsector of all of this, where both sides are really easy to understand, and you can really get your hands on things and check things concretely. So precisely on both sides, we're going to select certain states which are preserved by supersymmetry. Now on the gauge theory side, well, why is that easier? You'll find it has no coupling constant. The gauge theory is basically free. It's very, very simple. And on the gravity side, we find that the gravity side is a topological string, but it's also much easier to understand than the physical string. So in this context, in these subsectors, we can perform exact computations to try to match both sides. And as I mentioned, the ADS3 holography in Gabriel's talk is a different, not unrelated context where exact results can be obtained. So there might be some parallels with Matthias's talks. Let me zoom out. I'll be able to, so you guys can see a little bit more of the text. Is this legible or is it too small?
No, it's good.
Can I zoom out a little more?
I think maybe it's the good size. Maybe if you make it smaller, it would be a little bit too small.
Right. I just didn't want to just kind of be scrolling too fast. Okay. So the starting point of all of this analysis of twisted supergravity is the concept of a twist of a supersymmetric gauge theory. This was introduced by Witten in the late 1980s, a pretty famous work in which he related n=2 gauge theory to the Donaldson invariance of a Poor manifold. So I'm going to start by reminding you of how one builds the twist of a supersymmetric gauge theory. So the example we'll start with will be a 4-dimensional quantum field theory with n=2 supersymmetry. So let me remind you what it means to have n=2 supersymmetry. The group spin 4 is, well, an Euclidean signature, it's SU2 times SU2. So each copy of SU2 has its fundamental representation. And these are the two spin representations of spin 4. They're of complex dimension 2. And I'm going to use Penrose's notation for spinners. Spinners in S plus will have an index, a Greek index alpha, like this, and an S minus, they'll have a dotted index like that. Now, when we have an n=2 theory with n=2 supersymmetry, we're going to have two pairs of supercharges. Q alpha I, where I goes from 1 to 2, and Q alpha dot I, where also I goes from 1 to 2. So we should recall that the vector representation complexified vector representation is a tensor product of these two spin representations. So in Penrose's notation for spinners and gamma matrices, instead of having an index for vectors, we write a vector as having a pair of indices, one dotted, one undotted. So the x alpha alpha dot indicates a vector. Now the commutation relations with the supersymmetry algebra is simply q bar is delta ij times translation in the direction of this vector. Okay, so what does it mean to twist? If I have a theory with n=2 supersymmetry, well, I have two pairs of supercharges with this extra index I. And we want, so the superalgebra has a symmetry rotating that index. It's an SU2 symmetry. It's called the OR symmetry. So we're going to assume that our field theory also requires the symmetry. So the twisting procedure says that we're going to change the spin of our fields by using the SU2 OR. Now recall that spin 4 is a product of two copies of SU2. So I'm going to change the spin of the fields by, instead of making SU2 plus act in a normal way, I'm going to make it act via the diagonal map between the original SU2 plus and the OR symmetry. So what does that mean? That just means that, whereas before I had an index I in my supersymmetry algebra, I'm now going to make that index transform onto the Lorentz group So it transforms as the index alpha. So that whatever supercharges become, Qi alpha becomes Q alpha beta, where again, alpha beta are now spinor indices, and Q bar alpha dot I becomes Q bar alpha dot alpha. We'll use that in a minute, but you notice that Q bar now transforms as a vector because it has two spinor indices of opposite helicities. So what this means is that because the I index now transforms as a spinor index, we can build a supercharge, which I'll just call Q, which is a scalar. And it is automatic that in the supersymmetry algebra that this is a nilpotent supercharge. The reason is, well, if I take Q squared, the square of any supersymmetry is a vector, but this is also a scalar, so it must be 0. So the key point of the twisting procedure is that given the supercharge Q of square 0, we change the theory by replacing the original Hilbert space by the Q cohomology. So the twisted Hilbert space is defined to be those states which are in the kernel of Q modulo those which are in the image of Q. And we do this for everything else. We do this for local operators. Of course, if it's a CFT, that's the Hilbert space on the 3-sphere. It's a bit more challenging, but it is also possible to formulate this definition for extended operators. If one reads the older literature on twisting, the part which is really emphasized is the first step. This part here, changing the spin of the fields. But for me, I don't think that does very much. In fact, it does absolutely nothing. All that's happened in step 1, when I've changed the spin of the fields, especially if I'm on flat space, is I'm just calling things by a different name. Instead of having an index I decide to call it alpha. But I still have the same number of fields. My Hilbert space is still the same. My Hamiltonian is the same. All of the complexities are there. However, step 2, where I've replaced my Hilbert space by the Q cohomology, is a really radical simplification. And this is what allows you to do computations in the twisted theory. So, let's go. What I've described is the Donaldson-Witten twist of n equals 2 supersymmetric gauge theories. And it turns out to be a topological twist. So let me try and explain what that means. Although maybe, unless anybody has any questions about the material so far. Sorry if that was awkward.
Hello, can you hear me?
Yes.
So you had the index I for the SU2R and an index alpha for the SU2 plus. Why are you allowed to call them the same letter and then treat them as if they're in the same space? Because you take a trace at some point in defining Q, right? The scalar.
Right. That's right. So what I've done is I've changed the way SU2 plus acts on everything. So the charge of SU2 plus is the original charge it had before twisting, plus how it transforms under SU2R. So that's, let's scroll up a little bit. So I'm taking this step. So my new action of SU2 plus is the original action of SU2 plus, but then I embed it diagonally in the product of these two groups.
Yeah, I see. Thank you.
Okay, so let me move to, unless there are further questions, let me move to explaining what it means to be topological. So the hallmark of a topological theory is that the energy momentum tensor vanishes. So energy is the action of translation in time on the Hilbert space, and momentum is the action of translation in space. So let's explain why these operators vanish. When I twist, my Q bar supercharges, the index I becomes an index alpha. So it looks like this, Q bar alpha dot alpha. So it transforms as a vector. And if one looks at the original commutation relations, we take our supercharged Q, call Q is like, looks like that. When I commute it with Q alpha dot alpha, well, the only thing it can really become, if one thinks about the symmetry, is the operator of translation by the spacetime vector x alpha dot alpha. So what this means is that on the Q cohomology, this translation vanishes. So I didn't write out the equation that does that. So if I take a state psi, which is Q closed, then its derivative, if I hit it with translation in some direction, looks like this. Because here, if I'm the term where I move the Q past the Q bar is 0 because Q psi is 0. And this is equal to 0 in cohomology. So that's why I actually wrote this for local operators. The same thing holds. If I have a Q closed local operator, then if I try to move it around, it's Q exact. So what this means, if I'm studying the correlation functions of Q closed operators, they're independent of where I put them. So let's see this explicitly. I'm assuming all my operators here. I'm assuming these guys are Q closed. And I differentiate with respect to the position of the first one. Now, I move the derivative inside the bracket, and I replace it by QQ bar, get QQ bar of the first one there, and then the other ones. And because Q is a symmetry, I can distribute Q over the other operators instead. But they're all Q closed, so that's 0. So this is a summary of Witten's construction of the late 80s, that by performing this topological twist procedure, we find special operators have correlation functions which are independent of position. This is a very unusual feature, and it's a hallmark of having a TFT. Now, soon after Witten's construction, people thought about twists which were not topological. And that's going to be the focus of my lectures. So in the mid-90s, there was work by Johansson, Nekrasov, and others, where one studies the holomorphic twist of a theory with n equals 1 supersymmetry in dimension 4. So this particular example is not going to really be the focus of these lectures, but I'm just going to spell it out to demonstrate how twists can be holomorphic theories. Now, if one only has n equals 1 supersymmetry, then we no longer have the index I in the supercharges. We just have the supercharges are just consist of two spinors, one of each ellipsoid. So here, whatever we do when we twist, you can see it's not going to be possible for the twist to have the full spin 4 symmetry we started with. Whatever supercharge I select will break that. So we're going to break the supersymmetry to SU2 minus. Where SU2 minus rotates the Q bar alpha dot and fixes the Q alpha. So I'll take my supercharge Q to be Q1. So just one of the two components of Q. And then I'm going to write holomorphic coordinates on spacetime by Z alpha dot is X alpha dot 2, and Z bar alpha dot is X alpha dot 1. These are so what's going on is that once I've broken the Lorentz symmetry group to SU2, that SU2 preserves a complex structure in spacetime. Well, and here we can think about this should be a bar. The key thing we needed earlier was that Q bar would give me all of the translations. Here, what we find is that Q bar only gives you 2 of the 4 translations, those in the directions I call Z bar. So now, what does this tell us? The same argument tells us that correlation functions are independent of Z bar. So d by dz bar, say, for 1, if I differentiate the Z bar direction, the first coordinate, by the same argument, I bring this inside, I replace it by Q bar, and I move Q around, that's going to be 0. So the correlation functions are holomorphic functions of the position. So this equation here this is the Cauchy-Riemann equation. So one spends some time, it's interesting to study the behavior of these holomorphic twists. There's lots of fun things one can say about them. And in general, the most general behavior would be something that's partially holomorphic and partially topological. But let's not get into that. This is mostly an example. Now I want to move to the kind of twists we're really going to be focusing on to do twisted holography. It's illegible. So I want to focus on a construction which seems a little odd at first, whereby one starts with a 4-dimensional theory, an n equals 2 theory, which you assume is super conformal, and then you turn it into a 2-dimensional chiral theory. So this is a little bit funny. It's a little bit of a different thing than we did so far. There are 2 approaches to this. One is, which is perhaps the most widely studied, instead of taking Q to be a supersymmetry, you take it to be in the larger algebra of the superconformal symmetries. And the second approach, which gives you the same answer, is to use a version of Nekrasov's omega background construction. I'm going to spend a bit more time on this one. So Nekrasov did really kind of a still version of this. This particular omega background construction is due to G1O and Jen-Yagi. So this construction is a bit more technical than what I've described so far. So I'm not going to give all the details. So mostly what I want to do is explain the answer. You give me an n equals 2 theory, we will be able to figure out what the two-dimensional chiral theory is, and then we can do computations with it. So let's take an n equals 2 theory in dimension 4. Actually, maybe I should pause. Are there any questions, maybe? Or?
Hi, I have some questions from the beginning. I got a little bit lost. So by the twisting, do you mean working on the Q homology of the Hilbert space?
Yes. Working the Q homology of the Hilbert space and the space of local operators.
Okay, and I think that after that you mentioned that after performing this twisting, we preserve a complex structure, right? What does it mean physically?
I think it depends. So this was the case with n equals 1 supersymmetry. And the complex structure arises by noting that if I take correlation functions of Q closed operators, they only depend on half of the coordinates. So in Euclidean signature, they depend on certain complex combinations of the coordinates, which are called Z, and they don't depend on Z bar. So the complex structure arises, just from that equation. Let's see. Does that helpful for you?
Yes, more or less. And well, so the fact that our correlation function is holomorphic, is that a consequence of the twisting and a consequence of this preservation of the complex structure, or aren't they related at all?
Let me see. They're related. It's the preservation of the complex structure, the fact that spin 4 is broken to SU2, maybe maybe we should put that aside for now. And then the most important thing is that the correlation functions are holomorphic functions. And that statement is just a formal consequence of the supersymmetry algebra. It's just that d by dz bar is the commutator of q with something. So that's all.
Okay, thank you.
So in the n=1 example, can you say in a few words what is the set of operators that you're left with? Because I guess it's larger than the Carrel ring of the theory.
Yeah. Let's say we start with, let me find some blank paper. Okay, n=1 Carrel multiplied. Then we're left with one bosonic field and all its derivatives in Z1 and Z2, and one fermionic field and all of its derivatives. So if you look at the index of this, these are exactly the states that contribute to the superconformal index. Like for, this one gives you kind of product 1 over 1 minus q L, 1 minus p L, so on and so on. This kind of thing. But by looking at words in this field and its derivative, if you take its character with respect to the group U2, which is a symmetry because it's conformal, you'll find it's the standard index of an n=1 superconformal theory.
I see, thanks.
So maybe this is a comment for the experts. I think this is really interesting because suppose you wanted to give a careful proof of Seiberg duality, what you really should be doing is looking at the states of the twisted theory and identifying all of their correlation functions. That's kind of accessible, but also really not trivial at all to do. It's the kind of thing Davide is looking at this kind of question. Okay. We're up here. Okay, are there any more questions? Okay, so let me try to explain this construction of Yankee and O. So here I wrote down the n=2 supersymmetry algebra again. And I'm going to do something a little funny. We're going to take Q, which does not square to 0, squares to a particular transformation. So I'm taking epsilon to be a small parameter. And I write my Q as a linear combination of like this. And if you see, just by contracting the tensors, I think maybe the indices, my notation is not super clear possibly, but if you can just contract the tensors when you can be Q squared, you find that Q squared is epsilon times the translation. But if you look at the norm of this vector, you'll see it's epsilon times the space-like translation. So what we'll do is make this direction periodic. So really, we're working on this cylinder, which has coordinates x1, 1, x11 dot x22 dot across another plane which has coordinates x12 dot x21 dot. And it'll be important in a moment that here d by dx12 dot is q exact. And this other plane will be where the chiral algebra lives. Oops. So I'm going to call x12 dot z, and it's a holomorphic coordinate on this plane. Okay, so the result is, okay, I'm going to take my cylinder here, and I'm going to fill it in so that it becomes a cigar. So at the tip of my cylinder goes along and the radius shrinks. I got this cigar geometry. And then the result is that your n equals 2 theory extends across this cigar in a way which still preserves the supercharge we're using. So if we do this, we can do the following trick. So above, we saw that q squared was d by d theta. So that's rotation on the cigar. If I take an operator which is at the tip of the cigar, it makes sense to ask that that operator is rotation invariant. It's uncharged under rotation. And on such operators, q squared is 0 because q squared is rotation. So then we can consider the q cohomology of the S1 invariant operators at the tip. And this is going to be the chiral algebra. So what's important for this construction is that it doesn't make sense to move my operators away from the tip of the cigar. Because away from the tip of the cigar, q squared is rotation, and there are no rotation invariant operators. So this is why we've effectively localized to a two-dimensional theory. Now, on the plane, which lives at the tip of the cigar, d by dz bar is q exact. So for the same reason we've had before, if I take, it's like this, I'm taking things which are at the tip of the cigar and at other points, vi, in the plane, then the z-bar derivative of the correlation functions vanishes. As long as my operators I'm inserting are q closed and rotation invariant. So in this way, we have identified in our 4D equals 2 theory, which must be super conformal, something very familiar, a two-dimensional chiral theory, just like one might be familiar with from elementary studies of the bosonic string or something like that.
Sorry.
Mm-hmm.
Can you consider also extended operators on this cigar, like a line that wraps the theta cycle and so on? Did they give something interesting in the 2D or the?
Yeah, that's a really good question. So the answer is yes. So what happens is, if instead of thinking about it as a 4D theory on a cigar, we'll compactify to a 3D theory along that circle, the effective 3D theory becomes topological in the bulk with a chiral non-topological boundary condition. But there are extended operators, and these become the bulk operators in the 3D n equals 4 theory. From the 3D n equals 4 perspective, they're the ones which parameterize the Coulomb branch. So they're kind of subtle, and you realize that their 4D uplift must be the 't Hooft lines wrapping that cigar.
Okay, thanks.
Okay. So let me very briefly mention a different perspective. Perhaps it might have been better to explain this one, but for my purposes, I kind of didn't want to get into that much detail about either way of doing it. I mostly wanted to say the answer. So the different perspective developed by Beam, Lemos, Fiendo, Pillars, Brastelli, and Van Ries, they say that instead of taking an ordinary supercharge, like we've been doing, they take a superconformal charge, which lives in this superconformal algebra, which in this case is PSU 2,2/2. Now, what they find, things in the superconformal algebra include rotations. So in their story, rotations in one of the planes will be exact. So that implies, if you think about it, that the operators that live in the cube homology only exist on a plane inside of O4. Just like we saw above, the operators only lived at the tip of the cigar. Then they take the cube homology, and it's the same chiral algebra. And this perspective was historically the first one on building the chiral algebra from n equals 2 theory. And there's a great deal of literature about it, so I'm sure people who are interested in it can find good things to read. But as I said, I mostly want to say, given n equals 2 theory, what is the algebra? So let me start on this. If we have a Lagrangian theory, then we can just write down the algebra completely explicitly. So we'll start with the simplest thing, which is an n equals 2 free hypermultiplet. When one has n equals 2 supersymmetry, the smallest number of scalar fields one has is 4. So I'll write them like this: phi I, phi bar I. And this notation is kind of selecting, is breaking the symmetry in some way. And the Lagrangian for the free theory is the simple form, like this. Okay, so what do we get when we take the chiral algebra in the way I've just discussed, or at least a sketch? These 4 scalar fields of the n equals 2 theory become 2 scalar fields in the chiral algebra, beta 1 and beta 2. Beta and the beta i's comes from the phi i's, and the phi bars don't contribute. These are of spin half. So the OPE between the beta i's is beta I of 0, beta j of z, beta j of z is epsilon ij times 1 over z. So it's a little funny because so the beta i's are bosonic, but the OPE is like that of free fermions. So this chiral algebra is called symplectic bosons because they're bosonic fields. Okay. Now, what happens for gauge theory? Well, the n equals 2 vector multiplet contributes some fields to the chiral algebra. And these are something that should be quite familiar to people who've studied string theory. They're BC ghosts. Although, in contrast to the BC ghosts of string theory, these are ghosts that implement gauge symmetry. They're not ghosts that implement the diffeomorphism invariance of the roll sheet. So the BC ghost consists of BN, which is a spin 1 field, and CA, which is spin 0. And these are both fermionic. They have the simple OPE. The B times C is delta AB times 1 over Z. Same OPE one finds in free fermions, except they're spins 1 and 0. As in any ghost system, one has to add on the BRST charge. And the physical Hilbert space or space of local operators will be the BRST cohomology. So here is the formula for the BRST charge. And again, it might remind you of something you've seen in the string theory literature, except it's a little simpler. And the final thing one wants to do is consider how to couple the matter content to the gauge symmetry. So all we do is we add the fields from the matter to the goes from the gauge symmetry and build a BRST charge, which forces gauge invariance. So for the matter, well, if I started with a single hypermultiplet, I would have two fields, beta 1 and beta 2. So the most general picture is I should take my beta I, my matter fields, to be in a representation which is symplectic. So that means that I have some invariant tensor omega ij, which is antisymmetric. So I'll give you some examples later. Using the fact that G acts on the representation, we can build a current here. This is the current which generates the action of my gauge fields on the matter. And then we say the BRST charge is just that for the gauge theory plus the C ghost times the current. So I'm running out of time. We'll have time for questions at the end. Okay, so what we find is this construction works. Right, the BRST charge squares to 0 if and only if there's some trace identity, which is twice the trace in the adjoint representation of 2 of the algebra elements is equal to the trace in the matter representation. So again, you might be familiar with such a computation from, there's something like this in Polchinski. One more, in the bosonic string, BRST charge squares to 0 if and only if for the critical dimension. This computation is much easier. I'll give you the computation in just a sec. But the useful fact is that this is the same trace identity one needs to guarantee that a 4D n = 2 theory is superconformal. Let me move down to do the computation. So from the gauge sector, we have this vertex. And I want to consider the OPE of this with itself. So there's going to be a contribution from tree level involving 1 with contraction. This vanishes by the Jacobian entity. The 1 with contribution looks like this. I'm going to have C fields on the outside like that. Recall the legs correspond to a width contraction. They connect to C and a B because the OPE of C and B is 1 over Z. So let's compute this. We might have a contraction like that, and a contraction like that. Well, because there's 2 contractions, I get 1 over Z squared. A 0, CE, Z, and then let's include the flavor indices carefully. There's going to be twice times the trace, the adjoint representation, TATB. The factor of 2 is because B and C run around the loop. So let's take this expression. We notice C is fermionic. CA0, CB0, trace TAB is equal to 0 because this expression here is symmetric. So if we take the OB and expand in series, we find the first non-zero term looks like CA0 derivative CP0 to trace T TA to B. Now for the matter sector, it's going to be the same kind of calculation. the C ghost is going to couple to two matter fields. And we're going to do a Wick contraction where all the matter fields are contracted. And we find 1 over Z, CA, del CB, that's trace in the matter representation, PATP. And to be careful, this one came with a minus sign because they were fermions, and the other one comes with a plus sign. I take my BRST operator. This is as no O if this condition holds. And the final thing to ask, maybe I should have said this first. Why does a pole in the BRST operator and the OPE of the BRST operator with itself have to do with the BRST operator failing to be nilpotent? Well, if I compute the commutator of its interval, when I move the contours past each other, we'll pick up a term where one of them is integrated around in a little circle around the other. Like this. That said, the other one goes around like that. And if we look on the right-hand side of this expression, a first-order pole in the OPE of the BRST operator with itself will contribute a term in the square of the BRST charge. So this is not equal to 0 unless the trace identity holds. Okay, so I'll stop there.
Okay, let's thank Kevin. And